Hello, and welcome to the video accompaniment for Chapter 13, Section 1 of our text. In this video, we are talking about trees and their fundamental properties. So what are we going to get out of this video? Well, we're gonna understand and give examples of the following terms: tree, forest, and leaf. And then we'll work to understand this relationship between these three properties of a graph of order n and size m. So G being connected, G having no cycles, and the size being one less than the number of vertices. So sorry, edges being number of edges is one less than the number of vertices. So being able to understand how those ideas come together to give us trees, and we'll summarize that in a theorem. All right, let's get started. So first off, what is a tree? What's the definition of a tree? Well, that's a tree is a connected graph with no cycles. So what this is saying is that any graph that satisfies these two properties, so that it's connected and it has no cycles. So remember cycles, so like for example, cycle on 3 vertices looks like this. Cycle on 4 vertices looks like this, right? We can list out their vertices and know that they're the adjacencies, that we can do this sequentially, right, or cyclically, and we'll know how the adjacencies look. So like C5 then would be something like this, 5 vertices, cyclically connected like this. So this is saying connected graph with no cycles. All right, so what are some examples of trees? Well, here's a tree. Maybe I'll draw one more guy off of it there. So this graph is connected and it doesn't have any cycles in it. So how could I introduce a cycle into this? What do I mean by having a cycle? So what if I had this edge in there? Then these 3 vertices would form a cycle inside of my graph. So what I mean by no cycles is that there's no cycle, which is a subgraph of my graph. So I can't find any one of these cycles, or C6, C7, any cycle at all inside of my graph as a subgraph. And so that this, oops, and so this this edge here then would introduce a cycle between those 3 vertices, and we don't want that. So how else could I screw this up? It's a tree right now, but what if I don't know, drew another component to it? So now I have 2 components. If this is my whole graph G, now it has 2 components. That is, it's not a connected graph, and hence it wouldn't be a tree in that case. But as it stands right there, it's a tree. How else can a tree look? I'll draw something that's called a rooted tree. And actually, this will be a special kind of rooted tree. So something like, you might have even, likely you've seen a structure that looks like this before. And maybe I'll just have one vertex coming up there. This is useful for like decision trees, like if my answers are just yes or no, or if there's just 2 options, and the idea being that we proceed from the top to the bottom of the tree and answer questions along the way, ending at one of these leaves. I'll tell you what a leaf is in a second, but ending at one of these leaves, which would be the final outcome of my decision, what I should pick. So this is also a tree. Notice that it's connected and there are no cycles. If I introduced an edge like this, then notice I would have a 5 cycle here. That would prevent it from being a tree. But without that edge, this thing is a tree, and it is connected. There's not multiple components to this. So these end vertices, you might call them end vertices, that are in this tree, or these ones in this tree. So any vertex of degree 1 in a tree is called a leaf. Of course, why wouldn't it be? So these are all leaves. Is a vertex of degree 1. All right, how else could a tree look? I mean, it doesn't have to be, it doesn't have to be red from top to bottom. Maybe we have something that looks like, I don't know, something like that. There's another example of a tree. It's both connected and it doesn't have any cycles. We could even have something simple like just a path on 3 vertices. This is a tree. It's connected and doesn't have any cycles. Or what about just a path on 2 vertices? That also is a tree. And in general, a path is a tree. It's a type of tree. And we could even have a 1 vertex tree. So just 1 vertex with no edges. This would be connected, and it certainly doesn't have any cycles in it. But this would be an example of a trivial tree. It's a tree, but it's not gonna really fall in line with the rest of these, just because there's so little going on. So we say that's trivial. It's technically a tree, but it's more trivia than anything else that it's a tree. It doesn't really fall in line with the rest of this stuff. So we've talked about leaves. Notice that in any of these trees, I can find at least 2 leaves. P3, I can find these 2 leaves. P2, it's just on 2 vertices, but each one of these has degree 1, and so those are both leaves. And this one I can only find, well, that actually doesn't have any vertices of degree 1. But that's trivial, right? It doesn't follow the pattern of the rest of these. It's going to turn out that every tree actually has at least 2 trees in it, with the paths being the minimal amount of leaves, satisfying the condition that it has the smallest amount of leaves possible. That'll be a path. Notice something else. In each one of these trees, I'm going to find the order and the size. So I'll use N and M for that. N will be the order. So this has 4 vertices, right? And how many edges does it have? It has 3 edges. All right, I'm going to go to this next one, this bigger tree. I just want to compute these 2 values for each one of these trees. Over here, all right, how many vertices do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So here N equals 14. And how many edges do I have? I'll start at the bottom this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 edges. I'll go to this one. How many vertices? There are 10 vertices here. And how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 edges. Are you seeing anything with this? So here N is 3, and M, it has 2 edges. Here, number of vertices is 2, and it has 1 edge. Even with the trivial tree, N equals 1 and M equals 0. So even the trivial tree is following this pattern that the number of edges is 1 less than the number of vertices. So this is another property that we'd like to prove. Why is this the case? So 1, we'd like to prove that every tree has at least 2 leaves. And then we're actually going to use that to prove this fact that the number of edges is always 1 less than the number of vertices in a tree. So that'll be cool. We'll see that. And this will give us tools for detecting when something is a tree. All right. Sorry about that. It's what this says is a forest is actually, I've already talked about this. How about I just get rid of these just so we can read this? Because I've already talked about it. All right. So a forest, it's tree-like in that it has no cycles. But what is a forest in real life? Well, it's a collection of trees, and that's what a forest is in graph theory too. So it's a connected or disconnected graph with no cycles. And so if I had a graph, say, like this, and then this is still part of the graph, but another connected component, and then maybe something like this would be an example of a forest, because while it has no cycles in it, it's not connected. And so it's right. So when we do have a forest, it means we can break it into trees, that we can look at the connected components and each one will be a tree. So that's sort of a special property of a forest. And this will come up in one of the proofs we'll do. Okay, so you might be wondering why we should be even thinking about trees. So for that, I do have an application video after this. What I'd like to tackle in this video is just proving some of these results that we've noticed. So this relationship between order and size, the fact that it has every tree here has at least 2 leaves, except for this trivial tree. And in general, how we can recognize a tree. We'll prove some results for that. So let's summarize. So the question really becomes, what properties do all trees possess? We're studying trees in the abstract so that when they are applied, we have a base of knowledge that we can use about them. And this knowledge will turn out to be very useful when we're practicing with trees in the real world and actually applying some of these things. So the first one, yeah, we'd like to prove this. Every tree has at least 2 leaves. We're going to use that to prove that every tree of order n has size n minus 1, that result that we saw, that relationship. So we're going to prove that works in general. And actually, this should say, no, this is good. And then what we're going to do in terms of recognizing and understanding properties of trees is we're going to prove this theorem, which is really a collection of theorems. And that is, if we have a graph of order n and size m, and it satisfies just 2 of these 3 properties, then we know it's a tree. And since we know it's a tree, it'll satisfy the other property as well. So every tree is going to have these 3 properties, and if it has 2 of them, then we know it must be a tree. And so, for example, well, G is connected and G has no cycles. Well, that's just the definition of tree, so we already know that would be a tree. But what if it has no cycles and this that same relationship between order and size? Well, then we're going to know that it is a tree and that it must be connected. Or, for example, the other possibility here is that G is connected and has this relationship between order and size. Then again, we'll know it's a tree, and a cool result there will be that, oh, G must have no cycles. And so you see how we can put these 2 of these properties together and get the third one. And so we get a lot of bang for our buck with this theorem, but it's gonna take a couple theorems to prove it. All right, so let's move along. All right, so why does every non-trivial tree contain at least 2 leaves? So non-trivial, again, this is going to be the order is at least 2. So let's start proving this thing. And I'll say let G be a non-trivial tree. So that is I don't really need to specify the order and size for this one. Non-trivial tree. And so that's just telling us that it has at least 2 vertices in it. I'm actually going to call it T. I don't want to call it G. We know it's a tree, and we just want to show it has 2 leaves. So what I'm going to do here to find these 2 leaves, so let me maybe draw an example first and give us an idea of a proof strategy. So here's, I don't know, here's a tree. I'm trying to just make it kind of arbitrary, just a random tree. Well, the idea that we're going to do is we're going to take a longest path in this thing. Since it's a tree, we know it's connected. And so between any 2 vertices, we can find a path between them. And so we'll be able to find a lot of paths in this tree. And what we're going to do is we're going to take a path of maximum length. So while there might be a lot of paths in this thing, so like maybe from here, from here, the purple doesn't show up very well. So maybe we start at this vertex and move here, and then move here. So there's a path inside of it, but it's not a path of maximum length because I can find something longer than that. So here to here to here to here. So basically, we want to find a path in here that can't be extended further. And the notion of that, or what that tells us then, if it can't be extended further, that these end vertices of the path must actually be leaves. Otherwise, we could extend them further. And so let's write down a proof of that. That's going to be our strategy, and we'll see how the fact that the tree doesn't contain any cycles works into that. So let T be a non-trivial tree. Let P be a path in T of maximum length. So just imagine we in our random tree, or whatever our tree happens to be, we're gonna look at a bunch of paths and we're just gonna find one of the maximum possible length. Then what we want to do is we want to say that that those end vertices of the path are leaves. So let's give some names to these vertices on the path. Say P equals, remember path is a sequence of vertices, so I'll write it like this. So let's say it's V1, V2, Vk is the path. So those are the vertices of my path, and I'd like to claim that V1, so this would be like V1, and over here would be like Vk. And so here K minus 1 would be the length of the path. Remember, the length of a path is the number of edges. And I'd like to show that V1 and Vk are end vertices, right? So suppose V1 and Vk are not vertices of degree 1 in T. So that's my claim, is that these vertices that I found are not degree 1. So, all right, where do we go from here? If one of our n vertices is not of degree 1, so let's just pick on V1. So I'm going to say we may assume V1 is not degree 1. Why can I assume V1 is not? Well, if it's VK that happens to not have degree 1, then I'm just going to flip my path around so that V1 does. So no matter what, I'll just assume that V1 is not degree 1, and we'll see what happens there. So one of them is not. Why not V1? V1 is not degree 1. Then V1 U is an edge for some U. So for some other vertex in my tree, I must be able to find this vertex U in my tree that V1 is adjacent to, right? If it's not degree 1, I know V1, V2 is already an edge, so I can say here where U is not equal to V2, because we know that's already an edge. So we're saying there's some other edge coming off of V1. Well, okay, if U is not in my path, so if U is not a vertex of my path, then I'm going to make this path P prime, where I'm going to go U, V1, V2, and then take the rest of the path. And I know I'm not going to encounter U here, so I know it's really going to be a path, right? I don't repeat any vertices because I know that U is not in my original path. And so that would be, is a path of length. Let's just say more than P, right? I have one more edge. It would be a path of length K, and my original path is length K minus 1. So it would have one more edge, and that's a contradiction. I assumed that this path had maximum length, right? I picked the one of maximum length, which is a contradiction. And so in particular, I know that this case can't happen, that U must be on the path. So U must have been in the original path. But I know that V is adjacent to U, or V1 is adjacent to U. And so let's say U equals V sub I for some. So remember that U is not V2. So this would be for some I between 3 and K. Well, that means I'm going to have a cycle, right? So here's my, let me try and draw this for you. Then I would have, so I'd have V1 is here, and I know I go V2, V3, dot, 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 dot. I know this connects up, or does not necessarily. I know I might have some other vertices here, but here I am. I know I end with V sub K. And so no matter where this new edge goes to, this edge UV1, which I'm assuming is there, no matter where it goes to, it's going to introduce a cycle, which can't happen because we have a tree. Then T contains a cycle. Another contradiction. And so what this is saying then is that, remember my assumption here was that V1U was an edge for some other edge. So my assumption was that V1 is not degree 1. And I went through all the possibilities that came off of that and noticed that we got a contradiction in any case. And so it must be that V1 does have degree 1. And so then the same logic can be applied to VK. We can do the same exact argument with VK and conclude that VK must not be must have degree 1. So V1 and VK, hence V1 and VK have degree 1 as desired. These are the leaves of the tree. All right, there we go. There's the proof. So you might be wondering why we care that a tree has at least 2 leaves on it, other than just it's interesting. So so long as it's a non-trivial tree, it'll have 2 leaves. And so really the main purpose of that result is as in a lemma for this result, that every tree of order n has size n minus 1. So this is clearly a pretty useful result. It means if we know the number of vertices in a tree, we know how many edges it has, and vice versa. If we know how many edges it has, we can figure out the order. And so the fact that a tree has 2 leaves gives us a tool for induction. So the idea here is, this is sort of a proof strategy. So we'll take an arbitrary tree, and we want to prove that it has a certain number of edges. We know what the order is, but we know that it has at least 1 leaf on it. I mean, we know it has at least 2 leaves, but we're only going to use 1. We know it has at least 1 leaf on it, and so we're going to take away that leaf. What that's going to leave us with is a smaller tree, so 1 less number of vertices, with 1 less number of edges. And we know it has 1 less number of edges because this leaf, this was a leaf. So when we take it away, it just removes that 1 edge. And by our induction hypothesis is going to be on the number of vertices. That because this graph has 1 less number of vertices than the original graph, our induction hypothesis is going to kick in and tell us how many edges this thing has. And then we'll just be able to add 1 to that to figure out how many edges the original graph had. And this is going to give us our result. So that's the proof strategy. We're going by induction on the number of vertices. And so I'll write that by induction on the order of the graph. So that is, if we have a tree of order n, then it has size n minus 1. So we need a base for this induction. And remember, we can only use this leaf result if we have a non-trivial tree. So we just need to get rid of that case of the trivial tree. So on the order of the graph, let's let this be n. Let's call n the order of the graph, right? T has order n. Okay, so if n is 1, then any tree of order 1 is trivial, and that is it's an isolated vertex. It's just a single vertex by itself. So something like this, and that which has no edges. And so in that case, m, the number of edges, is 1 less than the number of vertices. And so it holds there. So this establishes a base for induction. I'll say, so we have a base. And so what we'll assume is that assume every tree of order k has k minus 1 edges for some k greater than or equal to 2, since we got rid of the trivial case. And so what we'll do is we'll give ourselves an arbitrary graph of k, or an arbitrary tree of order k plus 1. Let T be a tree of order k plus 1. And so the idea is we're going to show that, let's say, want to show that T has k edges, and then we'll be done. Since T is a tree, let U be a leaf of T. Since it's non-trivial, we can find this leaf. And consider T prime, which is going to be the graph obtained by taking T and removing the vertex U, so removing a leaf. Then T prime has how many edges? It'll have 1 less number of edges. Well, wait. Right. Time has 1 less edge than t, right? We know that because u is a leaf, and the order of t prime is one less vertex, so is order k. Okay, great. So we know by induction, every tree of order k has k minus 1 edges. It's k. Since t prime is a tree, by induction hypothesis, I should say a tree of order k, our induction hypothesis tells us that, the induction hypothesis, t prime has k minus 1 edges. Hence, so look at what we know now. We know that it has k minus 1 edges and it has one less edge than t. So how many edges must t have? Well, one more than t prime, which was k minus 1. So t must have k edges. Hence, t has k edges. That's what we wanted to show, that t has k edges. Done. And so we can say then that every tree of order n has size n minus 1, and this is why. All right, that's pretty neat. Let's see what else we can prove about trees. So you may be wondering, after that last theorem, that if we know a graph has this relationship between the order and size, that n equals m minus 1, do we know that the graph's a tree? And the idea is not all the time. We need some other condition on it to be guaranteed to be a tree. And so this is one of those conditions. So if we do have a graph of order n and size n minus 1, so that meets that relationship, and it has no cycles, then G has to be a tree. So those two properties together tell us it's a tree. So here I'll work out I guess just a proof sketch. I'll just kind of sketch this one out. You can look at the book to see all of the details of this. So what's the deal here? Well, I'm going to assume I have a graph of order n and size n minus 1 and that it contains no cycles. And I'd like to show, right, in order for this to be a tree, remember a tree is a graph with no cycles that's connected. So if I can prove that it's if I can prove that the graph is connected, then it must be a tree. So I'll say proof sketch, we want to show if G has order n and size n minus 1 and no cycles, then G is connected. Because connected and no cycles implies it's a tree. And so then I'll be done. So what's the idea here? So if G is a connected, or has no cycles and order n and size n minus 1, what I can do is, well, I guess what do we know about a graph with no cycles? We know it's a forest. A graph without cycles is a forest. So it looks something like, our graph will look something like, this. It'll consist of a bunch of trees that are disconnected. Something like this. This would be an example of a graph that we're looking at. And so it has these connected components to it. And since we know it has no cycles, each of the connected components, since it's connected, must be a tree. And so we'll take our graph G, and we'll look at the connected components where each one is a tree. So like T1, T2, T3, T4. And so we'll let, since we know each one of those is a tree, we'll know that it has size one less than its order. And when we add those all up, we'll see that, oops, there must have actually been only one connected component to it. That is, it must have been connected. So we're sort of assuming it's disconnected and then showing it actually should have been connected. So you can think of this like a proof by contradiction, or just us, or, we don't even need contradiction. We can just say, all right, it's a graph without cycles, so it has some number of components. If possible, it only has one component, and we'll show that it actually just has one component. So for each one of these trees that we have, we can know its order. We'll just go through and find the number of vertices. So each one of these is going to have order n minus or n sub I. In general, right, we'll have some blob here that's a tree t sub I. So we'll call that t sub I, and it'll have order n sub I in general. And so we'll call these number of vertices, or just order. That's the order of each one, and then we'll know its size because each one is a tree. So this would be n1 minus 1, n2 minus 1, n3 minus 1, n4 minus 1 in general, and I minus 1. And so we should say where we end this. So I'm going to draw one more tree here. I'm going to call this TK. So let's say it has K components. So I'm going to write that part down. Let the connected components of G be T1, T2, up through TK. So it has K connected components. Finally, we'd have n sub K and n sub K minus 1. Well, then, since we have all of these components, we can add up all their orders, and we can add up all their sizes to find the order and size of my original graph. So that is that n equals the sum from I equals 1 to k of all these n sub i's. So that's the same thing as n. And then we can add up their sizes. M, the order of the graph, or the size of the graph. Did I say that anywhere? Size m, let's say m equals n minus 1. So m, which is n minus 1, then must be the sum of all of the edges in the connected components. So this is the sum of n sub I minus 1. And let's just work out that sum. I'm going to split it up. This is the sum from I equals 1 to k, n sub I minus I equals 1 to k of just 1. Well, that sum is k, right? I'm just adding up 1 k times, so that's just k there. So this is the sum. So this sum is k, and then this sum here, well, that's this sum here, and so that's n equals n minus k. And so that is, notice here that I have n minus 1 equal to n minus k. And hence, k must equal 1. Remember what k was? K was the number of connected components. So that means that G only has one connected component, and that must mean that G itself is connected. So G is connected. Hence, it's a tree. And so there's my proof sketch for that one. So in that last theorem, we were able to prove that if a graph has that order size relationship, n equals m minus 1, and it has no cycles, then it must be connected and is therefore a tree. So what if it meets that order and size relationship and it is connected? Can we conclude that it has no cycles and is therefore a tree? Yeah, in fact, we can. So let's take a look at a proof sketch of this one. So we'll give ourselves, we're actually going to do this one by contradiction. So let's give ourselves the hypothesis. We'll assume the hypothesis is true. So let G be a connected graph of order n and size n minus 1. And assume, so we're going by contradiction, assume G has, but I don't want to assume it's not a tree. I mean, I want to say that a little bit clearer. So remember, if we can prove, remember, connected and no cycles means it's a tree. Implies that it's a tree. And so if I can just manage to show it has no cycles, then I'll be good. And so I'm going to assume it does have a cycle. And the proof strategy here is if it does have a cycle, I'm going to remove an edge from that cycle. And the special thing about cycles is that when I remove an edge from them, I'll still have a connected graph afterwards. Now, there's no way to disconnect a graph by removing an edge from a cycle, right? I mean, imagine I have a graph that looks like this that contains, that cycle over there, or maybe it has a couple cycles. If I say remove one of the edges from the cycle, I'll still have a connected graph. And even if it has another cycle, I'll remove an edge from that and it'll still be connected. So the idea is I'm going to take a graph with this order size relationship and the fact that it's connected, and I'm just going to remove edges from cycles until I arrive at a tree. Or really until I arrive at a graph with no cycles. And since I know that it's connected, I know that resulting graph will be a tree. But then we'll see something goes awry, right? We're looking for a contradiction here. So assume G has a cycle. Let E1 be an edge of that cycle. Then I'm going to call it G1, which is going to be my original graph minus that edge E1 is connected because I removed an edge from a cycle. So it leaves a connected graph is connected. If it has no more cycles, then we can stop. So if G1 has no more cycles, stop. So we're sort of presenting this as an algorithm. If G1 has a cycle, then find E2 on the cycle and remove it. So I'll remove E2 from G1 and let G2, which will be connected. Again, because it was an edge of a cycle. So like up here, right, I started with this. I removed this one because I found a cycle and I found some edge on it. And then it still had a cycle, and so we can remove any edge from that cycle. And in this case, with the tree I have up here, with that example I've been working with, we would be able to stop at this point. So eventually, so keep doing this, arrive at GK, which is going to be G minus this set of edges, E1, E2, EK. And so what's going to be its order and its size? Well, we didn't remove any vertices. All we did was remove edges. So it has order n and size. Well, how many edges did I remove? I removed k. Remember, it's possible k is 1. That's okay. That means we stopped right here, and then k would be 1. So if order n and size. So we started with, it had size n minus 1 and size n minus 1, and then we removed k edges from that, n minus 1 minus k. However, GK has no more cycles, right? We kept doing this until we had to stop, until there were no more cycles. However, GK is a tree, and GK has order n. So size of GK, that is n minus 1. So, well, that's impossible. We assumed it had at least one cycle. And so that was basically saying then that k has to be greater than or equal to 1, the number of cycles. K had to be greater than or equal to 1. But n minus 1 minus k then would be, n minus 1 minus k would be less than or equal to n minus 2, since k was at least 1. And that's a contradiction. So n minus 1 can't be less than or equal to n minus 2. So this is a contradiction. Hence, G has no cycles. It follows that G is a tree. All right, so we've proved a couple results here about this relationship. Let's summarize these in another theorem. All right, so just to summarize all those results, if G has any of these two, or any two of these three properties, then we know it must be a tree and have the third property. So connected and no cycles, that's just the definition of a tree. And so we proved this result that says if it's a tree, then it has that. If G is connected and has the order size relationship, we were able to show that it has no cycles. Remember, we kept removing edges from cycles and showed that we shouldn't have been able to remove an edge in the first place, and that it must have had no cycles. So we proved that result, and we also proved that G has no that if G has no cycles and this order size relationship, remember in this one we were able to show that it had to be connected in that case, right? That the number of connected components had to have been 1, and therefore the original graph was connected. And so really, those theorems that we've proved can all come together to imply this theorem, which basically is a summary theorem. It's a collection of results that gives us a nice way to think about trees. And now we have this, quite a useful result. It gives us ways to detect trees and really tells us what are the fundamental properties that trees possess.